So this is the 29th video on relative velocity. This is in continuation of the 28th video. In the 28th video, two numerical problems on relative velocity collision were discussed. So in this video, we'll discuss more problems similar to the second problem of the previous video, 28th video. Similar problem, okay? So it will be explained in more details. Fine. So first I'll write down the question. So P1 and P2 are two moving points. P1 and P2 are 2 points moving along line joining them. Line joining them. And P1 is to the left of P2. Fine. Accelerations of P1 and P2 with respect to ground are constant. Of P1 and P2 with respect to ground, G meaning ground, is constant and equal to 5A leftward arrow, meaning 5A leftward and A leftward respectively. That is, P1 is moving towards left with a constant acceleration 5A with respect to ground, and P2 is also moving leftward at a constant acceleration A with respect to ground. This bracket means leftward arrow means leftward direction. Fine. Also, initial speeds of P1 and P2 are u1 and u2 respectively. So three possible values of u1 and u2 are given. Fine. So for each of the cases, three cases are given. Three cases are given. First case is this. P1 is moving at a speed of 6u rightward and P2 is moving at a speed of u rightward. This is the initial speed of P1 with respect to ground, 6u rightward and P2 u rightward. Part B, P1 is moving at a speed of u leftward and P2 is moving at initial speed of 9u leftward. And C, P1 is moving at initial speed of u rightward and P2 is moving at a speed of 6u leftward. These are the initial velocities and initial speeds of P1, P2 and their motion directions. Fine. So now accelerations of these 2 points are common to all these ABC. Alright. Now what we have to do, we have to tell in each case ABC what is the minimum value of u so that the 2 points subsequently collide. Each of A, B and C to find the minimum value of u so that the 2 points collide. Okay. So this we have to solve. So for each of these ABC, accelerations of these 2 points are same data has to be used, 5A left and A left. Alright. So this is the main problem. So I mentioned the problem now. So what we'll now do is that we'll solve it by the relative velocity concept. So this problem is again similar to the second problem of the 28th video. So we are discussing just for the sake of more practice and more familiarity with the concepts. Okay, fine. So now I'll rub this. Okay. So this problem will solve by the use of the concept of relative velocity. Fine. Okay. So this is solved by the concept of relative velocity. So we solve the problem either as seen from P1 or as seen from P2, whichever we want we can take it. Okay. So we'll solve it as seen from P1. So solved by as observed from, solved as P2 observed from P1. Solved as P2 observed from P1. So we'll solve it as seen from P1. Fine. So now first point which I'm repeating, accelerations of these 2 points are as given for all the 3 cases. Okay. So what we'll do is that first we'll find the relative acceleration of P2 with respect to P1 in ground frame for all the 3 cases A, B, C. So we write in this way: A, P2, P1, G, meaning relative acceleration of P2 with respect to P1 in ground frame. That is same as A2G minus A1G. A2G is the acceleration of P2 with respect to ground, and A1G is the acceleration of P1 with respect to ground. Okay. So this I'll write here. So A1G as given just now, which I rubbed just now. A1G is just given to be A1G is given to be 5A left. And A2G is given to be A left. So P2 P1G is the relative acceleration of P2 with respect to P1 in ground frame. That is A2G minus A1G. A2G is A left, so this is A left. And this can be written as plus of minus of A1G. Minus A1G is just the reverse of A1G. Okay. So A2G is equal to A left, and minus A1G is equal to 5A right. So we add these two factorially to get A relative. So these two have to be added factorially from parallelogram law of vector addition. This will be 4A right, which is a constant. Quantity. Fine. So relative acceleration of P2 with respect to P1 in ground frame is constant, 4A rightward. Okay, it has a constant magnitude of 4A and a rightward direction it has. Okay, so this is constant. So we'll call it just equal to, we'll denote it by A relative say, which is a positive constant. Fine. So this is the first part which has been fully explained. All right. So now one more thing. In all the 3 cases, P1 and P2 are moving along a straight line joining them. So motion of P2 with respect to P1 will also be along the same straight line. Okay. So since P1 and P2 are moving along common line joining them, implies that relative motion of P2 and P1 will also be along the common line. Relative motion of P2 with respect to P1 will also be along the same line. What does this mean? This will mean that P1 will observe that P2 moves along the same line joining these 2 points. Okay. This means that with respect to P1, P2 also moves along the same line. Moves along the same line. Okay. So this means that, so first observation is that relative acceleration of P2 with respect to P1 in ground frame is constant, that is 4a rightward. And second observation is that since P1 and P2 are moving along common line joining them with respect to ground, therefore as seen from P1, motion of P2 will also be along the straight line joining these 2 points. Okay. So that means that with respect to P1, P2 will undergo a rectilinear motion with a constant rightward acceleration of 4a. Alright. So this means with respect to P1, P2 moves rectilinearly. Rectilinear meaning straight line. At a constant A relative equal to 4a rightward and initial relative speed u relative. This u relative will be different for A, B and C, different cases. Fine. So this is the basic observation till now. Fine. Alright. The first observation is that relative acceleration of P2 with respect to P1 in ground frame is constant, 4a rightward. And second observation is that with respect to P1, P2 will move in a straight line at a constant acceleration of 4a. And initial relative speed of u relative, value of u relative will be different for A, B and C. Fine. So this means that since A relative is constant and straight line motion is taking place P2 with respect to P1, so we can apply those 4 formulas for constant acceleration along straight line. V equal to u plus at, d equal to ut plus half at square, v square equal to u square plus 2ad, d bra u plus v by 2 into t. So we apply the third formula. So we write v relative square is equal to u relative square plus 2a relative into d relative. U relative is the initial relative speed of P2 with respect to P1 in ground frame. A relative is just 4a rightward. D relative is the relative displacement of P2 with respect to P1 in certain interval. Okay, fine. So now what we'll do? That we'll take up the 3 cases A, B, C separately. This much part was common to all of 3 of them. Okay, this much part was common to all the 3 of them. Alright. So this I'll rub it now. Fine. So now what we do, u relative is the initial relative velocity of P2 with respect to P1 in ground frame. So that is from the theory of relative velocity between 2 points, u2g minus u1g. That is just equal to u2g plus reverse of u1g. We add these two vectorially to get u relative. Alright, fine. So now u relative is equal to u2g plus minus of u1g. Alright. So now we take the 3 cases separately. In first case, speed of P1 is given to be how much? 6u rightward. And speed of P2 is given to be how much? Speed of P2 is given to be u rightward. P1's initial speed of P1 is 6u rightward. And initial speed of P2 is u rightward. So in this case now we have to find the minimum value of u so that the 2 points collide. So this much part which is common, I am writing it here. Okay. So in this portion we will write like this. V relative square equal to u relative square plus 2a relative into d relative. Okay. So now first determine u relative. U relative is just this quantity. So this formula we have to apply in this case. So u relative vector is nothing but vector sum of these two. U2G and reverse of U1G. Minus U1G is the reverse of U1G. Alright. So what you write this as? This will write as U2G. U2G is what? U rightward. Alright. And U1G is what? U1G is 6U rightward. Minus U1G will be 6U leftward. We had vectorially these 2 points. Vectorially we add. By the law of vector addition, this will be 5U leftward. Alright. U rightward, 6U left. So 5U leftward. Okay. So this means, see, that this means that time 0, what is this? Time 0, P1 is here, P2 is here, P2 is moving at an acceleration of, constant acceleration or rightward acceleration of 4a with respect to P1, and P2 in this initial separation is L. P2 is moving at initial relative speed of 5u leftward with respect to P1. Okay. So this is the situation at time 0. Fine. Now one more thing we have to note down. Since u relative and a relative are in opposite direction, so since u relative and a relative are in opposite direction, are in what? Opposite direction, implies that relative speed between these 2 points decreases as time passes by. This downward arrow means decreases, upward arrow means increases. Fine. So since they are in opposite direction, v relative decreases as time decreases. So now see, initial relative speed is 5u left and rightward acceleration of P2 with respect to P1 is constant 4a. Since they are in opposite direction, v relative decreases. So now see, 2 cases arise, sub cases. First is that as P2 moves towards leftward towards P1, its relative speed with respect to P1 goes on decreasing. So one possibility is that P2 does not reach till here, it reaches somewhere till here and then its relative speed becomes 0. Then what will happen? When P2 comes here and its v relative vanishes, but still its relative acceleration is rightward, so it will begin to move rightward. So there will be no collision again. Okay. So if v relative is 0 before P2 reaches P1, then what will happen? P2 will come to rest somewhere here with respect to P1, and because its rightward acceleration is still 4a rightward with respect to P1, it will begin to move rightward. So this will mean there will be no subsequent collision. But we have been asked to find the condition for collision. So this means before P2 reaches P1, v relative vanishes. Then there is no scope of, no possibility of any collision. Okay. So this means that if collision is to take place, then relative speed of P2 when it reaches P1 should still be more than 0. So for collision to take place, relative speed of P2 with respect to P1 when P2 reaches P1 must be greater than 0. Okay, then only collision can take place. So not what we'll do now, we'll apply this formula. Fine. Now we know that in this formula u relative, v relative, a relative, d relative all have to be taken with proper sign. So we follow the convention that this is P1, this is P2, left side is positive and right side is negative. So v relative square, relative speed of P2 with respect to P1 when it reaches P1, so that is v relative, so v relative square. U relative, as we have found just now, is 5u, okay. It is just equal to 5u left, okay. So 5u left whole square. A relative acceleration of P2 with respect to P1 in ground frame. This you know it is how much it is. This is just equal to, it is known to be 4a. Fine. P1 with respect to P2. Okay, yes, 4a. 4a rightward, so minus 4a according to the sign convention. And v relative is what? Relative displacement of P2 with respect to P1 in ground frame when P2 reaches P1. Now as seen from P1, P1 is at rest. P2 is moving towards it. So when as seen from P1, P1 is at same location. P2 is coming from here to here. So this means the relative displacement of P2 with respect to P1 will just be equal to how much? L towards left. So plus L. Plus L. And this relative square should be positive. That is the condition for collision. So 25u square is more than 8al हो गया. U is more than root under 8al by 25. So this is the minimum value of U. This is just the minimum value of U, okay? So U minimum will be equal to root under 8al by 25. If U exceeds this quantity, then collision will take place. If U is just equal to this quantity, then it will be a limiting case. Just when P2 reaches till P1, its relative speed becomes 0. That is just a limiting case. And if U is less than this quantity, there is no scope for any collision at all. Fine. So this is the part A which has been fully solved. Alright? Okay? So I'll rub this, okay? This part A has been solved. Now we solve the part B of this question, part B. I will rub this, okay? Now we take part B of this question. In this U1, U2 is different, fine. So this quantity is P1 is U left initial velocity and P2 is 9U left. Okay, fine. This is the initial data, P1 and P2. Again, in this case, we have to find the minimum value of U so that collision takes place. So in this case, again, we find U relative first. So U relative becomes U2G. U2G is how much? 9U left. And vector sum of minus U1G. U1G is U left. So minus U1G becomes U right. We take the vector sum of these two. This will be 8U left. So U relative is 8U left. Fine. Again, at time 0, what is the situation? At time 0 situation is this. P1 is here, P2 is here, L distance away. It has a constant rightward acceleration of how much? It has a constant rightward acceleration of 4a with respect to P1. And initial relative speed of P2 with respect to P1 is 8U left. Now again we see these two are in opposite direction. So in the opposite direction, the V relative will what? Decrease as time passes by. As time passes by, V relative will go on decreasing. So again, two possible cases arise. One case is that P2 comes to rest with respect to P1 before P2 reaches here. Somewhere here the V relative becomes 0. Then what will happen? If V relative becomes 0 here, then because its relative acceleration of P2 is rightward, it will begin to move again in rightward direction. Then it will begin to move away from P1. So there is no collision. So if V relative becomes 0 before P2 reaches P1, implies there will be no collision. So this means for collision to take place, relative speed of P2 with respect to P1, that is V relative, should be non-zero when P2 reaches here. So for collision to take place, V relative should be 0 when P2 reaches P1. So for collision to take place, V relative should be 0, more than 0 when P2 reaches P1. So now what we do, again we apply that formula for constant acceleration as mentioned just now, we have discussed it. So we apply the formula V relative square equal to U relative square plus 2A relative into D relative. So U relative is just how much? 8U left. It is just equal to 8U whole square. That is again with sign. Leftward left of P2 positive, right of P2 negative. A relative will again be minus 4a, as has been discussed. Okay, minus 4a. And D relative is the relative displacement of P2 with respect to P1 when P2 reaches P1. Now as seen from P1, P1 is at rest. P2 is coming from here to here. So D relative displacement of P2 with respect to P1 is L towards left, that is plus L according to our convention. Okay. Now this V relative should be more than 0 for collision to take place. So 64u square minus 8al should be more than 0. U should be more than al by 8. This is the minimum value of u, so that collision takes place. The part B of the question has also been fully solved. Fine. Now I'll wrap this, okay? And now we take the part C of this question. In part C, it is given that initial speed of P1 is u rightward and initial speed of P2 is 6u leftward. Again what we do, we find u relative in this case again. We again determine the value of u relative. So what do we write? U relative velocity of P2 with respect to P1 in ground frame initially. That is just equal to u2g plus reverse of u1g. Fine. And u2g is what? U2g is 6u leftward. u1g is u right minus u1g, that is reverse of u1g will be u left. We have to add this to vectorially. So this will be 7u left. Okay, fine. This will be 7u left. This is u relative. And a relative is how much? 4a rightward. So they are again opposite direction. Since they are opposite direction, this implies V relative decrease as time passes by. So this means again two subcases arise. So first subcase is that V relative becomes 0 before P2 reaches P1. That is like this, something like this. P1 is here, P2 is initially here. Somewhere P2 comes here till here and its V relative becomes 0. Then still relative acceleration of P2 with respect to P1 is rightward 4a. It will begin to move rightward. So there is no scope for collision. So only again for collision to take place, V relative should be more than 0 when P2 reaches P1. This way again as we have done in part A and part B. So for collision to take place, V relative should be more than 0 when P2 reaches what? P1. Again we apply that constant acceleration formula, third formula, which we have been applying for part A and part B. So we write V relative square equal to U relative square plus 2A relative into D relative. V relative square, U relative is how much? 7U left. So this is 49U square. A relative is minus 4A as mentioned. D relative again we write as plus L as we did in part A and part B. So this should again be more than 0 for collision to take place. So U should be more than root under 8AL by 49. This is therefore the minimum value of U. Fine. So this is the third part of the answer question. Okay. Fine. So this is the 29th video. I discussed 3 problems of the ABC. Alright. If you go through these problems, then you will have a complete grip over the one-dimensional relative velocity problems. You must be expert in finding the relative speeds and relative acceleration between two moving points, especially when they are moving along common line joining them either in same direction or in opposite direction. Fine. So this 29th session we have discussed in this way. Okay. In successive session 30 and session 31 also, we will take up 2 more problems of this case. Then we will take up some different types of relative velocity problems. Okay. So we will close this session just now. Fine. All right.